All right, welcome to 5-3, talking about functions defined with definite integrals and the fundamental theorem of calculus part 2. So to sort of open this lesson, let's just talk about these three definite integrals right here that we're going to evaluate. So we have the integral from 1 to 2 of 2t dt, the integral from 1 to 3 of the same integrand, and then the integral from 1 to 5. So let's just quickly go ahead and go through each of these. Okay, so using the fundamental theorem of calculus part 1 that you just learned in the previous lesson, you would get the following. So notice for each of these, the antiderivative of 2t that we can get is t squared, and then we're evaluating that from 1 to 2, and then 1 to 3, and then 1 to 5. And then remember, you're evaluating it at the upper limit first, minus evaluating that antiderivative at the lower limit. And so we get 3, 8, and 24. So hopefully you noticed that for all three of these, the only thing that changed was the upper limit. And so if you really look at the work that we really did do the exact same steps every single time. The only thing that changed was that upper limit. The only thing that changed was that upper limit. And so what that means is we really could think of this definite integral as if it were a function where the independent variable was the upper limit. So in other words, I could think of the same definite integral as some function big F of x, which is the definite integral from 1 to x of 2t dt. And so really, this first definite integral that we did, from 1 to 2, that was really the same as finding big F of 2. The integral from 1 to 3 of 2t dt, that was really like finding the value of big F of 3. And this last one was like finding big F of 5. So this is actually something that you're going to encounter definitely on the AP exam, at least one place in the free response section, I would anticipate. So it's very common to define a function as a definite integral where your independent variable for the function, the variable that gets replaced by values if you're evaluating the function, is one of your limits of your definite integral. Okay, so one of the things that we can then realize is all of the work that we did here to get the 3, the 8, and the 24, remember, all of those steps were exactly the same. The only thing that changed was the value that we eventually substituted in the front. So I could actually evaluate this same definite integral, but leave it in terms of x. So in other words, remember, this would still be the antiderivative of 2t, which is going to be t squared, but now we're evaluating it from 1 up to x. And so now when I evaluate that, that's going to become x squared minus 1 squared. And so ultimately we just get x squared minus 1. So this original big F of x that was defined as a definite integral from 1 to x of 2t dt is really equivalent to this function here, x squared minus 1. So notice big F of 2 would be 2 squared minus 1, which is 3. Big F of 3 would be 3 squared minus 1, which is 8. Big F of 5 would be 5 squared minus 1, which is 24. So that's exactly how I got all these different values, and notice how integrating this definite integral gives me this other version of the function just in terms of x, but no longer as an integral. Okay, so here's an example. So we're going to find big F as a function of x, and then we're going to evaluate it at x equals 1, x equals 4, and x equals 8. So here our big F of x is defined as the definite integral from 2 to x of t times 3t plus 2 dt. So just like before, first thing we're going to do is we're going to go ahead and simplify that integrand so that we can actually work with it. So this is really the integral from 2 to x of 3t squared plus 2t dt. All right, so now we can find our antiderivative of 3t squared plus 2t, and that's just going to become t to the third plus t squared. I did skip a step there. This is technically 3t to the third divided by 3, so the 3's divide out. And then this is going to be 2t to the second divided by 2, so the 2's divide out. And then this is going to be from 2 to x. And so we get x to the third plus x squared minus 2 to the third plus 2 squared. And that's going to become x cubed plus x squared minus, now this is going to be 8 plus 4, and so finally we get x to the third plus x squared minus 12. So this right here is our capital F as a function of x. So now that means if I'm trying to find big F of 1, well, that's really the integral from 2 to 1 of t times 3t plus 2. But remember, to evaluate that, all we're really doing is we're substituting into our new function that we just found. So that's going to be 1 cubed plus 1 squared minus 12. And that's going to be 1 plus 1 minus 12, which is negative 10. Same thing for f of 4. So again, that's technically the integral from 2 to 4. But we're just going to substitute that into our new version of the function. So we have 4 to the third plus 4 squared minus 12. And that'll be 64 plus 16 minus 12. And that does give us 68. And then finally for f of 8. So again, this is really the integral from 2 to 8 of t times 3t plus 2 dt. But now we're really doing 8 to the third. That'll be a pretty big number there. Plus 8 squared minus 12. And don't worry, I would not give you numbers like this on a non-calculator section and expect you to deal with it, not because I don't think you can, but just because I don't want you to spend that kind of time doing that by hand. So this would end up giving you 564. Okay, so again, this was an example of a function being defined as a definite integral where your independent variable, the variable that you're replacing, is actually one of your limits of your definite integral. Okay, so one way that we can approach that is by actually finding the definite integral in terms of x, and that actually gives us an alternate version of the function that we can more easily evaluate. Here's another situation that will absolutely come up on the AP exam. So once again, we do have a function here. In this case, it's h of x. We have a function defined as a definite integral where your variable is one of your limits. So h of x is the definite integral from 1 to x of some function f of t dt, where f is the function whose graph is shown. So this graph made up of 3 line segments, this is f of t, or f of x, doesn't really matter. This is f of something. And we're trying to evaluate h of 1, h of 3, and h of 7. Now, unlike the previous example, I don't actually have a specific equation for f of t, so I can't quite approach this the same way that we did in example 1. But because I do have the graph, and because this graph does form regions that are geometric shapes, we can evaluate the definite integrals by using what we understand the definite integral to be, which is the area, or the net area. So in other words, if I'm trying to find h of 1, that's really the integral from 1 to 1 of f of t dt. Now, I don't even need to look at the graph. If you think back to Unit 4, remember with definite integrals, we had a property that said the definite integral from a to a. So if my limits of my definite integral match, remember that that's always just going to be 0. Okay, now the next one is h of 3. So that means I'm looking at the integral from 1 to 3. But remember, that means we're looking for the net area under the curve from x equals 1 to x equals 3. So that would actually be this region right here. Well, it's a triangle with a base of 2 and a height of 2. So remember, area is 1/2 base times height for a triangle. So this is going to have an area of 2. So that means this definite integral right here is equal to 2. And then finally for h of 7. Again, that's now the integral from 1 to 7 of f of t dt. So we're looking for the net area from 1 to 7. Now, remember, from 1 to 3, that was already positive 2. From 1 to 7, again, we've got this triangle down here. So this has a height of 3 and a base of 1, 2, 3, 4. So the area here is going to be 1/2 times 4 times 3, and that's going to be 6. So that triangle has an area of 6. But remember, that's area beneath the x-axis. So in terms of net area, remember we're subtracting any area below the x-axis. So h of 7 is really the amount of area above, which was 2, minus the amount of area below, which was 6, and we get -4. So sometimes, to evaluate a function that's defined as a definite integral, we might not be able to approach it the way we did in example 1, where we actually come up with the equation, because we don't actually have an equation for f. But if f is shown to us as a graph, then we can return to understanding that the definite integral represents the net area under the curve. Okay, now I'm going to repeat this in the assignment itself, but on your assignment for this lesson, when you get to problem number 3, that problem is divided into multiple parts, A through D. You are only doing part A. Do not worry about parts B, C, or D, okay? So again, I'll remind you of that, but I'm telling you right now. Okay, so now that we've looked at several examples where we had a function defined as a definite integral, now let's start moving toward what the fundamental theorem of calculus part 2 really talks about. So consider the function f of x equals the integral from 1 to x of 3t squared plus 2t dt. And the question for you is, what is f prime of x, big F prime of x? What's that going to be? So let's just do the same thing we were just doing here. So if I'm trying to find big F prime of x, then what I'm really doing is I'm looking for the derivative with respect to x of big F of x. But that means what I'm really doing is I'm finding the derivative with respect to x of this, the integral from 1 to x of 3t squared plus 2t dt. But now, let's go ahead and rewrite this integral as another function in terms of x, which you saw us do earlier. So again, I'm still trying to find the derivative with respect to x of, and then here, remember the antiderivative of 3t squared is going to be t cubed, plus the integral of 2t is going to be t squared, and this is from 1 to x. So now I'm looking for the derivative with respect to x of, so this is going to be x cubed plus x squared minus, remember it's 1 cubed plus 1 squared. So I'm really looking for the derivative with respect to x of x cubed plus x squared, and then 1 cubed plus 1 squared, that's going to be 2, so minus 2. Okay, so now we're just taking the derivative of that expression. Well, remember the derivative using the power rule, so the derivative of x cubed is just 3x squared, plus the derivative of x squared is 2x, and then the derivative of negative 2 is just 0. So we just get 3x squared plus 2x. And what I want you to notice is, look at what the derivative of big F of x turned out to be, and look at the integrand of how big F of x was originally defined. And I hope you notice some similarities there. The only difference is that the x that served as our upper limit has replaced the t's. But otherwise, it's exactly the same. And that's not coincidental. In fact, that's what the fundamental theorem of calculus part 2 tells us. So here's what the FTC part 2 says. So if f is continuous on an open interval containing some number a, then for every x value in that interval, the derivative with respect to x of the integral from a to x of f of t dt is just f of x. So again, what it should look like to you is the x, that's the upper limit, basically just got substituted in to your integrand f of t, and we just get f of x. And it's literally all this is. And what this is basically doing is it's verifying to us that derivatives and integrals are inverse operations of each other. So think about taking the square root of something being squared, and you just end up with the original. Or dividing something after multiplying by the same thing. So these two operations undo each other, and that's really what the fundamental theorem of calculus part 2 is verifying for us. So let's look at some examples here. Okay, so consider the function f of x equals the integral from -4 to x of t minus 6 dt. So we're going to first find f as a function of x, so that's like what we did in the beginning of the lesson, and then we're going to demonstrate the FTC by differentiating that function. So in other words, based on the fundamental theorem of calculus that I just showed you, we should already expect that big F prime of x is just going to be x minus 6. Remember, the x just substitutes for the t. So we should already expect that big F prime is just going to be x minus 6. But we're going to demonstrate that that happens by actually showing the integration and then differentiating that. So again, we're going to go ahead and find big F of x. That's the integral from -4 to x of t minus 6 dt. So that means, remember, we're going to integrate first. So the antiderivative of t is going to be t squared over 2, and then minus 6t, and that's from -4 to x. And then now, if I substitute, that's going to become x squared over 2 minus 6x, and then minus, now I have -4 squared over 2 minus 6 times -4. That's x squared minus 6x minus, now this is going to be 16 divided by 2, which is 8, plus 24, so that's going to be 32. So that's my big F of x. And then now, remember, we're going to try to find big F prime of x by finding the derivative of x squared over 2 minus 6x minus 32. Okay, so power rule says I'm going to move the 2 out in front, so that's going to be 2x over 2, which is just x, minus the derivative of 6x is just going to be 6, and then minus the derivative of 32, which is just a 0. And sure enough, there's the derivative. And remember, that's what we expected it to be. Using the FTC, we should have expected the derivative of big F to be x minus 6, and we verified that. Okay, so hopefully, now that you're convinced of the FTC, now we can just use it. So use the FTC to find big F prime of x. All right, so we have big F of x equals the integral from x to 3, from 3 to x of the square root of t cubed plus 2t squared dt. So if I'm trying to find big F prime of x, again, to use the FTC, all that I'm doing is I'm taking my x and I'm replacing my t's. So this just becomes the square root of x cubed plus 2x squared. And that's it. That's it. So let's do one more that's this basic. So we have big F of x equals the integral from pi to x of the square root of t secant of t squared dt. So again, as long as I notice that I've got a constant as my lower limit, doesn't matter what the constant is, in this case it's a pi, could have been anything, and as long as your upper limit is just your x, then we can just use the FTC straightforward. So f prime of x just becomes the square root of x times the secant of x squared. Okay, so nice and easy, right? So yes, there is a catch, but only if it's not set up exactly this way. So again, I want you to notice for both of these examples, our function was defined as an integral from a lower limit that was a constant up to an upper limit that was just x. So as long as that's your setup, then finding the derivative of that function is as straightforward as just replacing the t's with x. So what if it's not quite set up that way? So what if we have this instead? So big F of x is the integral from x to 2 of t cubed times the square root of t minus 4 dt. So hopefully you notice that it's almost what we want. I do still have that x as my limit for my integral, but it's the lower limit now, and my constant is my upper limit. And in order to use the FTC, we need the lower limit to be the constant. Well, you might remember from Unit 4 that I can rewrite this integral by flipping the limits. And remember, if I flip the limits, then it just makes the integral negative. And instead we get this. So now this matches what we wanted to have. We have the lower limit as a constant and the upper limit is just x. So now we can find big F prime, and that's just going to be the opposite, because that negative is now there, of x cubed times the square root of x minus 4. Okay, so if your function isn't defined exactly the way that we need it to in order to apply the FTC, look for a way to rewrite it so that it does match what we want. Okay, so what about this situation? So I have big F of x equals the integral from 1 to x cubed of sine t over t squared dt. So again, this is very similar to what we want. My lower limit is a constant. My upper limit does have an x in it, but the problem is it's not just an x. It's more than an x. And that should sound familiar to you. I'm trying to find the derivative, but instead of being in terms of just an x, it's more than an x. So in other words, it's almost like I'm saying this is really the integral from 1 to u, where u is x to the third. And what that should make you think about then is the chain rule. So what we really have here then is a derivative where I have to use the chain rule. So what that means is, to find the derivative of this, you're going to do the same thing. So the derivative of big F is going to be, so same thing, I'm going to start by replacing x to the third in place of the t's. So this is now sine of x to the third over x to the third squared. But because it wasn't just an x, it was more than an x, we have to multiply by the derivative of x cubed. So now when I simplify this a little bit, I'm going to have sine of x cubed over x cubed to the second. Remember, we multiply the powers there, so that's x to the sixth, times, and then the derivative of x to the third is 3x squared. And then we can simplify here a little bit. Those x squares cancel with 2 of those, and we just get 3 sine of x cubed all over x to the fourth. So again, in a situation like this, where your upper limit is almost just an x, it's actually a function in terms of x. So if your upper limit is more than an x, you get to do the exact same thing. You just replace the t's with that expression, but then you have to multiply by the derivative of that function in terms of x because of the chain rule. Okay, so that is the fundamental theorem of calculus part 2. All right, good luck.